Everybody, welcome and good morning and good evening in America. Today, we're very happy to have Dr. Casey Lisse, Lisse to give the first talk. Today, we have three talks. The first one now by Dr. Lisse, and the second one at 10 o'clock by Dr. Edward Lin, and to be followed by another talk by Dr. Xiaozhen Zhang. This talk by Dr. Lisse, let me first tell you that I met Casey first time at the very exciting time when people discover a very strong X-ray emission from comet. Yeah, and Casey, I mean, as usual, was the first one to jump in to make the interpretation, the correct one. So he did a lot of very pioneering work. But then before then, he got his bachelor degree from Princeton, and then master degree from UC Berkeley, and then he got his PhD at Maryland. Yeah, I think on some infrared study of cometary dust, right? Cometary dust tail.
Working with Micah Hearn. Mm-hmm.
Yeah, with his physics advisor was the great Micah Hearn. And since then, he had been working at I think you have never left the Maryland area.
Not for my work.
And anyway, he worked at the Space Science Institute, yeah, and then and of course associate with the University of Maryland, and now he's at the Applied Physics Lab as a principal scientist. And if you go to ADS and you find that Casey is still extremely active. Recently, he just published a paper on the formation of planetesimals, right, around some young stars. And I have that in my pocket. I haven't read it yet. Oh. Okay, so he's gone. And
oh, no, I'm right back. I just wanted to hold something to motivate you.
Okay, Casey. So here you are. Yeah, please go ahead. Thank you.
Thank you very much, Wing. It's a pleasure to talk to this group. I want to say is that I have no Chinese and I have English, and I may speak a little bit fast because I'm from the East Coast. And please, if you have any questions about what I say while I'm talking, it's no problem if you want to raise your hand and ask for a clarification. I'm very honored to talk to you all today. So I'm going to tell you about my experience with the New Horizons project. This is a NASA mission that did something that when I was a kid, when Professor Ip was a child, was absolutely science fiction. People, if you ever talked about flying to Pluto or flying past it, people would look at you and say, just stop reading books and get real. And now we've done it as humankind has done this. And it's pretty amazing to think about this. And this is the number one reason that I got into astronomy and into working. I was always looking up at the sky as a kid and wondering what was out there. And I get to do this for a living, which is just fantastic. And you can see a number if you can see my cursor, a whole bunch of my colleagues and friends. This is an applied physics lab. This is right after we flew by the KBO Arrokoth, MU-69. And you can see that they're all extremely excited because they're seeing brand new territory, places that have never been seen before, never been visited. And so absolutely fantastic. So I'm going to explain to you the little bit of background. What are Kuiper Belt objects? What is the Kuiper Belt? What was the New Horizons mission? What did it do? And then I'll explain what some of the most important findings, at least that I think. There's lots and lots of findings. And then I'll take questions. And I'll just point out, so Wing has already told everybody that I work at the Johns Hopkins University Applied Physics Lab, and I work on the New Horizons mission. I also work on a mission that is going to be launched in 2025 called Spherex, which is going to be an all-sky 0.7 to 5 micron spectrometer. That's job is to look at the first galaxies and try to figure out how the Big Bang, how inflation happened. Was it a single phase change or was it a multiple phase change? And I'm also working on a mission that's been designed by APL called the Interstellar Probe, which is going to go through the heliosphere out to the heliopause and into the nearby galaxy. So lots of interesting things coming down the road. Okay, New Horizons is the first dedicated mission to explore the Kuiper Belt. And the Kuiper Belt is the third zone, if you will, of the solar system. It's very, very large. And as I'm going to tell you later, it has most of the dust, mass of the dust, probably about 97% of it that is orbiting our solar system. It's extremely diffuse. The easiest way, again, as I'm going to tell you in a second or two, is it is the edge of the original disk that formed all the planets and the asteroids and the comets, everything in the solar system. It's the edge of what was originally condensed to make what we know and love. The amazing thing about the New Horizons mission is it's only been 85 years since the Pluto discovery, and only 20 years since the first Kuiper Belt object, other than Pluto, was discovered by Jewett and Liu. So it's actually, things are accelerating. This is actually a pretty fast reconnaissance so soon after these new objects, this new region of the solar system was discovered. And you're going to see this a bunch of times, but here is basically our launch path. We launched in 2006. We got a big kick going by Jupiter and saved ourselves 5 years, gravitational assist. And 9 years later, we flew by Pluto. And then another 4 years later, we flew by Arrokoth, which is also known officially as 2014 MU69. You'll hear me use both names for it. And we are currently out here. I'll show you where we are exactly today, because you can go and look at that for yourself at our webpage. A little bit of background. This is a very busy but very useful slide. You met Bob Brown at Space Telescope a number of years ago. And if you want to know how do solar systems form, a large mass of material, which is between the stars, gets forced together, starts collapsing. And mainly you would think of it as there's a bunch of gas in a giant molecular cloud. And when a supernova goes off, it can have more energy output and a huge amount of pressure than the entire galaxy combined. And intersecting supernova shock waves can start collapse of the gas and the dust between stars. And once the gas starts collapsing, it will start aggregating and it'll start condensing more mass and get more gravitational pull. And it can be a runaway process. It's also a very messy process. You'll notice that we only have about one solar mass here in the solar system. And most models say that it took 4 to 5 masses to collapsing to form what we have today. The other nice thing about this, I'm going to show you these cartoons, is that here you have real pictures of the different stages. So the propylids in the Orion Nebula, so this is the sword of Orion, you can see what look like collapsing clouds with baby protostars at their center. And this happens pretty quickly, this collapse. It happens in 10,000, maybe 100,000 years. And then in the next 100,000 years, any sort of spherical nature collapses because there's a net spin to the cloud into a disk with a protostar. You're starting to form the T-Tauri stage, and you get a lot of accretion still from the disk onto the star. But the accretion, also, there's a lot of angular momentum you also have to throw away, and that gets blown out into jets. So you have stars still growing from this spinning disk of material around it, which is collapsing and eventually going to clean out. Its remnants are going to make the planets over here. And you're blowing stuff out. And that's why you see these beautiful jets. And here's the disk of the system, HH tau. Now, this is all pretty fast in terms of astronomical timescales, 100,000 years. In the next few million years, you start making comets. Your T-Tauri star is settling down. It's mostly grown into what it will become as a star. It's still working its way onto the main sequence. You've got a lot of gas and dust in this primordial disk, and this is when you can make your gas giants. You're going to make your first planets fastest because collisions between particles and gas is going to go at roughly as the density squared. Density times density is the probability of stuff hitting and aggregating. And we're going to get into this later on too, by the way. And you're going to make your gas giants and probably within 10 million years. And you're also going to dissipate most of the gas in the disk in that time scale. Then you start making rocky planets like the one we love on and know and love. You do that somewhere between 10 and 100 million years. The asteroids, this is actually old. Now we think the asteroids were actually made very young, early over here. And that's because people have aged things like this. This is Campo, a meteorite I have in my possession. You make your terrestrial planets. We think that's what's going on. Beta Pic has recently made a giant planet. We think they'll also may be making rocky planets. And then eventually you clean out almost all the dust and gas in the system. You get the occasional meteor, like we still do. Earth is still growing about 10 to the 4 metric tons every year. And then you have a mature system with planets orbiting relatively quietly. The planets don't run into each other. They're not migrating. And you have a system like we know and love, or like TRAPPIST-1. Okay, so where does the Kuiper Belt come into this? As I'm going to tell you, the Kuiper Belt is the edge of this big fat disk here. There isn't enough stuff in the Kuiper Belt to make planets, but there is enough stuff to make snowballs. I'm having problems advancing. Okay, and I just told you a story and I gave you some pictures. Well, here's some more pictures. These are Hubble images of circumstellar disks around other stars. Every one of these images you're seeing is a Kuiper Belt. Asteroid belts would be inside the occultation spot here. They're much too small to be imaged. These are other people's Kuiper Belts. It's very cool to see them. This is one that I've actually published on. This Kuiper Belt is so narrow and dense, we think it's actually forming the planet, even as we speak, as we're watching it. And here's the famous Fomalhaut system, which may be doing something similar. But it's exciting to realize what we're looking at. Kuiper Belts happen. And because every disk has to have an edge, every single disk that I showed you here doesn't go to infinity, has an edge, has a finite edge, you can expect every system should have a Kuiper Belt at one time or another. All right, here's a different view of them. Remember, I was talking about the T-Tauri stage. So this is when you've got a young star that still has enough, the disk around it is still massive enough that it's still dumping material. The star is still growing. About 10% of the star is still in this disk. And the disk is very thick. There's all kinds of things going on. It's very hot right next to the star. And this is the paper that Wing mentioned, R.W. Rigay A, that he'll be reading. And in here, at the center of the disk, where the star can't really shine much light, it's very, very cold. And it's very cold, and here's our Kuiper Belt, the edge of the disk I mentioned, and this is where our objects are forming. And there's all kinds of interesting chemistry and physics that can go on there. I'm going to touch on it a little bit. We really don't have time in this talk to go into great detail, but I'll point you to some papers. But I wanted to set the picture for you. So first of all, you're starting with this thick disk. Eventually it thins out. You make those planets I mentioned. And then those planets, even after when things are still maybe 10, 100, few hundred million years, the planets are still got a lot of dynamical energy. They're still moving in orbits. They haven't settled down to like grooves in a record player like we see today. And they're going to do what's called migration. They can still gather energy and angular momentum from planetesimals and grow. And they can move because of that. If they grab one, there's a bunch of mechanisms. Very simply, if there's a Neptune grabs and accretes a planetesimal that's outside its orbit, it's going to tend to move outside the orbit because it's going to slow down. So there was a lot of migration. It's called the giant planet instability era. There are arguments about whether it was 100 million years or 600 to 800 million years, like the age of the craters on the moon, which happened during what we call late heavy bombardment. But that being said, you take the very simple picture of a very thick Kuiper Belt with all kinds of objects at the very edge of the disk, and then Neptune moves out, and Neptune says, you're either going to become part of me, you're going to help me grow, or I'm going to gather you up and I'm going to put you in what we call resonant orbits. Neptune goes around the sun, and it's going to grab objects that are going to go around 2 times for every 3 times Neptune goes around. And that's Pluto. These are the resonances here. You see these sharp gatherings. These are Kuiper Belts in certain orbits, and the number of spots you see is the number in a given kind of orbit. And these are the Plutinos. There are about 40 different objects that are roughly the same kinds of orbit as Pluto is. You also have what we call the scattered object, which Neptune just threw all over the heck, but they are still around today. And you have objects that just said, Neptune, go do what you want. We're really kind of far out. You're not going to mess with us. Neptune only went out to about 30 AU or so, right about where it is now. And like Arrokoth, Mu-69, they just have been going around the sun in the same orbit since they were born. And this picture has grown over the last 30 or 40 years. We saw pieces of this, and now we think this is all unified in that we now understand why there is a structure in the Kuiper Belt. And we also understand that the scattered objects can eventually, interactions with the giant planets, especially Neptune, can get thrown in on the order of 1 a century, and they can turn into what we call centaurs, and then into what we call comets. So this is actually the source of our short period comets, is this Kuiper Belt. There are these pink objects that are scattered, that Neptune long ago kicked out of their nice circular quiet orbits. And then every now and then, they come too close, given enough time, and they get thrown into the inner system. And Dave Jewett wrote a very nice paper in 2015 where he can actually look at the colors of the objects, very, very distant KBOs, to centaurs, to comets, to the sun. And there's a very, very nice progression. And actually see how they age and they change color. They go from very red to rather blue. So it's really nice to put this all together. We think we understand how this all came to be. Okay, so now I've kind of hopefully set the stage for you. There's a lot to read about this if you want. So I'm just giving you the introduction here. There's lots and lots of little Kuiper Belt objects. We think there's in the order of 1 million. The big ones that you probably hear the most about are these guys. These are the whole fight over whether Pluto is a planet. These are the dwarf planets. And I want to show, I'm not going to get into the argument. I just want to show you, this is Pluto and Sharon, going to be the stars of our show, along with Arrokoth. And this is the moon. And these are to real size. So don't go any farther. The Pluto and Sharon have a fantastic system. They're wonderful worlds, but they ain't that big. So all this fussing and fighting. And so what I meant before was I said that the objects out in the Kuiper Belt, they just didn't have enough mass and they haven't enough time to aggregate into one big body. There's lots and lots of very interesting snowballs out there. And as I'm going to show you, Pluto really does look like a fantastic world. So, okay, enter New Horizons. We have this idea, we've been looking with our telescopes, let's go out and visit these things. And every time we go but actually visit or fly through, we learn something. So here's New Horizons in all its glory. This is actually I'll talk a little bit more. Here's our big antenna. Here's our plutonium-238 radioactive electricity source. I'll go and show you the instruments. We launched on an Atlas V in 2006. And this is, if you see these pieces, that's actually the inside of this white nose, this fairing. So this is what protects you when we're flying really fast through the atmosphere. And this is the spacecraft on top of the upper stage rocket getting assembled in the clean area before it gets put on and put out on the launch pad. The spacecraft, if you want to get a feel for it, is the size of a small grand piano. It's no bigger than that. And you can ask, why didn't we do that? If you actually look at a spacecraft like Cassini was as big as a bus, a good-sized bus. But we had to get out to Pluto in a reasonable time. So what we literally did is we took the smallest spacecraft that was real highly functional and put it on the largest rocket we had and blasted off into space, the fastest ever launched from the Earth at the time. We are powered by a radio isotope thermoelectric generator because the solar panels were so far away from the sun. Solar panels are highly inefficient. So that's what this is. It this black is in order to help radiate heat. And so it's the alpha particle decay from plutonium-238 that is powering our spacecraft. We're down to about 150 watts now, and we have to be very careful. It's what's going to limit us eventually. We think we can get out to 80 or 90 AU before we're going to run out of power. We just heard that last week. We carry 7 science instruments. And they mass less than 1 camera on the Cassini mission to Saturn. And this, you're going to laugh, but we spent a huge amount of money at the time. You really probably will laugh, especially your kids and listening, or youngsters listening to this next generation. We spent extra millions of dollars to get 8 gigabyte solid state recorders. Because that was the state of the art at the time. And we knew that we still are data limited. We literally just got down some really good spectral data from Arrokoth in the last few weeks because we have to parse it and how we get back. The New Horizons instruments, there are 7. Lori is our basically white light camera. It's a big, large, clear filter, but that's all the high resolution images I'm going to show you. The Ralph suite has our color imager and infrared composition mapper. So it has 2 components. It has MVIC and it has Lisse, the spectrometer, which I'm also going to show you a lot of data from. We have a UV spectrometer called Alice. That's the PI's instrument. We have REX, that's this radio telescope. Not only sends all our data back, but also has done bistatic radar measurements. It has done thermal radar radio wave measurements of the surface temperatures of Pluto and of Arrokoth. We have 2 solar wind instruments, SWAP and Pepsi, low energy and high energy. And we have a student dust counter, which has now had like 6, 7 generations of students and has done the first counting ever of dust past Saturn and has discovered the Kuiper Belt dust belt, which is very important. I've already alluded to it a little bit. We've had quite a ride. It's been 10 years and 3 billion miles, at least to Pluto. I mentioned we launched in 2006. It was quite a bit of work in order to make sure we got off the launch pad in January 2006, because if we didn't, we wouldn't get the big kick from Jupiter. We flew really close to Jupiter and swung by it. And by doing that, we saved ourselves 5 years. And what you've seen this a little bit before, I'm showing you the reconnaissance. This is the image of the system from Hubble. This is all we knew about the Pluto and Sharon system before we got there. And there's 3 little spots that are for moons. And this is the incredible journey we've had for this grand piano. And we have gone to Pluto, we've gone past Arrokoth. We're now in the heart of the Kuiper Belt, in fact, probably a little bit past the middle of it. And we're hoping to find another object, but there may not be anything right in front of us left. Let's just say that on the way, we did some fantastic science. Oh, good, the movie is playing. This is Jupiter, and here you can see the shadows of one of the Galilean moons, actually 2 of them, on the surface of Jupiter. This is the great red spot, which in this color stretch is not red, it's yellowish. This is probably my favorite movie from the Jupiter flyby. This is Io. And if you look at it in true color, it has all the colors of sulfur and brimstone, yellow and red and brown. This is a giant 10-kilometer tall geyser. This is a sulfur oxide fountain because Io is the most volcanic place in the solar system. Hopefully I can get that bar will go away. But there are 3 different geysers. There's a little one down here. This is the big one. I can watch this for hours. Just to think, it would be fantastic to get up close and personal and visit Io. And there's another one, I think it's a bare one, it's hard to see here. And this is one of the giant craters, volcanic caldera. Io is just fantastic. And it's all because it is close to Jupiter and tides are ripping it back and forth and dumping a huge amount of energy. It's converting orbital energy into volcanic energy. Okay, so let's see if we can get next. So I just given you the highlights of Jupiter in one slide. This is the highlights of Pluto, but we're going to actually go into a little more detail. But this slide is so nice, I include it in this talk. Here is the Pluto Flyby, which happened. We got most of our data pretty much from the 13th of July and through the 15th, with the best data, of course, happening just within a few hours of the closest approach. And we got everything from, this is actually a look back image. We got this beautiful atmospheric haze, and this is real color. We saw incredibly dark, what looked like tholin, so heavy refractory organics that's in this region here. We saw the giant heart of Pluto that everybody's heard about. And in the left ventricle, if you will, we see huge amounts of what look like convection cells in N2 and methane-rich ice and CO-rich ice. We found cryo volcanoes. New paper by Kelsey Singer has just published on this. And here is the heart of the cryo, right Mons. We had also a good time naming all these places. So Mons is fancy geographer speak for mountains. And I worked with a lot of geologists, and I learned a lot because it's a very different discipline I'm used to. We saw the polar haze coming across the top of Pluto. You can see the beautiful structure. And I'm going to show you what we call the coffee table picture, which is even, by the way, made it onto a flash drive. Don't worry, you'll see it up closer and personal. We saw outflow in the heart. These glaciers actually look like they're coming and then they're going subducting. We see sublimation pits there as well. We've got composition from the spectrometer in conjunction with the LORRI white light images. And you can see that methane is all over, methane is all over. CO and N2 tend to concentrate in Sputnik Planitia in the ventricle, and water actually doesn't. Water is elsewhere. Well, on Pluto, water is actually is probably buried on most of Pluto, but we see it at what are the bare places, the hot, dark, organic, rich places. And then there's Sharon, which is an object. You should look here. Sharon, these are about real color. Pluto is roughly yellowish, kind of sepia, parchment colored, and Sharon is grayish. Sharon has a red spot on the surface, which we think is actually stuff emitted by Pluto and dumped onto it, methane, and then attacked by the solar wind and turned into polymerized heavy organics. There is water and ammonia all over Sharon. It has no atmosphere, as I'm going to show you. And these relative sizes are about real. Sharon is about half the size of Pluto. It's very big compared to its primary. And we're going to talk more about that. We were very excited. This is Jim Green, who has led the mission. What's funny about this picture is this is like 7:47 in the morning, and we have no idea if the spacecraft has survived. And that's me. These are all my teammates. We are wearing all kinds of, we have Pluto gear. I can show you that I'm actually got my fleece right here. We wear it to all the team meetings. It's actually I like the coloring. I'll put it on maybe for you later during the question and answer. We're all very excited. We know that the spacecraft has gotten to this point, but let's face it, you've just spent 9 years getting to Pluto. You're not going to immediately tell it to turn around and phone home. And there's like a 4 to 5 hour light travel time anyway. You wanted to do all its maneuvers and things. And then much later on at like 9 p.m., we got our first signals back. And we realized the spacecraft was safe. There was no damage from any sort of possible dust or hitting moons or anything in the orbit around Pluto, because it is a busy system. And we were absolutely ecstatic. 5 a.m. the next day, the PI gets us all up and back into APL. We're all tired and grumpy, and we see this image. And I think it's on cover of books. And we're all just flabbergasted. This is fantastic, brand new world in detail. And what's really funny about astronomers, I don't know how many of you worked with them in detail, we're all a bunch of what Americans would call nerds. We're all technical people. It took us maybe 30 seconds to get over being from a minute to be going, oh my gosh, this is gorgeous, this is brand new, to, hey, is that a mountain over there? Are those ice caps? What's going on over there? is that a giant fault system that's running up and down north and south? And immediately people started doing science on this image. And it's just fantastic to see how geologists can take, to my eye, which, well, you know, two-dimensional image, which has a lot of structure in it, and actually produce not physical scenarios, actually explain what's going on. And we're still doing that today. So let me set the stage here. This is what we saw looking at Pluto. Here's the North Pole, the equator's here. I mean, Pluto is tilted quite a bit off the plane of the solar system, and we're coming in at it. So this is the image we got the day side. You've already heard me talk about the different ices on Pluto, and the important, and we also noted very markedly that the dark light extremes were most marked around the equator. Well, Rick Binzel wrote a paper showing what the different regions of Pluto are, where how they will experience sunlight. And basically, these areas of the poles are just like our poles are Arctic. They can have times of extreme cold and times of extreme darkness and times of extreme light, dark and hot and cold, just like we do with the Earth's poles. But there's also regions, unlike the Earth, where the Arctic and the tropics can actually overlap. And I want to direct you to his paper. I can't spend too much time on this, but I do want to point out is that it's these very interesting regions where the day and night happen roughly equally is where we see all the real color variations, where we see the incredible dark, what looks to be the hot, high plateaus full of ortholans and water. And then we also see Sputnik Planitia. Pluto is also very round. We expected with Sharon over there and half its size to actually be very elongated and egg-shaped. It's not. It's about it. Pluto and Sharon are both round as cue balls, which says a lot about when they froze out. And it means that we're almost positive Sharon was formed in a giant impact. We'll hopefully talk about that a little bit later. It means that Pluto and Sharon were still very fluid and liquid as Sharon moved out far enough away that it didn't create much of a tidal bulge. Pluto is also the biggest thing in the Kuiper Belt, as far as we can tell, just barely bigger than Eris. It may still be a little bit less massive, but it's bigger in size. It also has an exobase. We're going to talk about this a little bit. It has an atmosphere, which is supported by evaporation from Sputnik Planitia. And when we passed by Pluto, it was closest into the sun as possible. So the atmosphere, Sputnik Planitia was the lowest. The pool had been drained, if you will, and the atmosphere was about as dense as it gets. It's actually settling down now. I promised you this picture. This is coming over the North Pole and towards Sputnik Planitia. And that two-dimensional kind of flattened image you saw here, here's looking at a grazing angle. And you can see incredible structure. You can see all these mountains. I also want to point you to this. This is the haze that I pointed out and showed you was blue and looking back. You see has all kinds of layers, which we think are gravitational waves. And especially has a very thick layer, which we think is also due to condensation when the atmosphere gets cold enough right above Pluto's surface. So all this is very fantastic. Again, there's a lot of papers we need to point you to. This is what a day on Pluto looks like. Here's our closest approach, but we weren't just studying it right at closest approach. We were watching it as we came in and went out. There are times, however, when we're farther away, resolution isn't anywhere near as good. But I think is fantastic, you can see the heart, if you will, rotating around Pluto. You can also see the much lower signal to noise when you're looking at the night side. Sharon, its moon, here's the North Pole and that dark spot I was mentioning, which we think is Pluto, if you will, dumping stuff on it. Sharon is also very round and half its Pluto size I mentioned. It has an ancient crater surface, which is very different. One hemisphere has almost no craters. Looks like there is a 4 billion year old lava flow has just wiped out almost all the craters. And then the upper hemisphere has all kinds of structure to it. And there's a giant chasm running along Sharon. Neither Sharon nor Pluto show any evidence of, I'm blanking on the word, compaction. They all look like they're extensional, which is very interesting because it tells us they're most likely not differentiated inside. They didn't make ice 7 in their center and then collapsed. Instead, they most likely they may be some differentiation, but they didn't create a global contraction. When we used Alice to look back, Sharon towards the sun, we saw 0 atmosphere. There is nothing here, which is very interesting. Sharon's, remember, only half the size of Pluto, but we think it was just at the boundary where it couldn't support an atmosphere. And because Sharon and Pluto formed, we think Pluto formed first and there was a giant impact by Sharon, it could have had its atmosphere stripped and it just wasn't big enough to hold any new atmosphere that would be created by outgassing from the interior, whereas Pluto could. This is what a day on Sharon looks like. I'm just going to go through this fast, but you can see beautiful structures rotating. We can go to this in question and answer period. because there's so much stuff, I hope you don't mind my flipping through this a little bit. This is the Pluto-Sharon system. Here's Sputnik Phoenicia. Here's their mutual axis. And I want to set this up. Pluto and Sharon are tidally locked, but they're not just tidally locked the way the moon, our moon, is tidally locked to us. We only see the same side of the moon. We never see the far side of the moon. And there's no such thing as the dark side of the moon. There's the near and the far. And the one side of the moon is always facing towards us, and it just rotates around every 28 days. Sharon, not only does Sharon also tidally lock that way, but Pluto and Sharon rotate with the same period that Sharon goes around Pluto. So that would be, imagine our moon is always showing us the same face, and the moon was always just over the Pacific Ocean, never moving in the sky. They are like two, if you will, ice skaters who are just locked in, just staring at each other and going around and around and around together. And that's very extraordinary. The fact that they are coupled so well with angular momentum, and the fact that this giant basin is now actually along this axis. So this led us to asking lots of questions like, was there a weakening here? Was there some reason, pardon me, there's a helicopter going by. Was there some reason why this basin happened here? We now think that what happened is that basin actually, the impact happened way off of this axis, and Pluto actually rotated to put that depression along the axis of spin between the two of them. This is the Pluto system through the eyes of New Horizons. This is what we look like to Hubble. Some nice little bright spots. We found no more moons than Hubble did, which was a little bit surprising. Also, testimony to the power of Hubble. But this is what we see. Of course, Hubble didn't give us any of this beautiful structure and understanding what's going on in these bodies. This is the 4 small moons, Kerberos, Hydra, Nix, and Styx. And 2 of them we got close enough to. Remember, we had to choose. We couldn't go by all 4. And we're going through the system almost like a bullseye. We went through, if this is the plane of the system, if it is in the plane of the image here, we went right through and passed between Pluto and on the other side of Sharon. We went through over here to stay away from any dust that Sharon could have collected. So we went through over here, so we only got near 2 of the moons. But what we did see was very irregular moons and also extremely bright, as if they were made almost of pure water ice, which is very interesting. It tells us about the impact that formed them. We're pretty sure that these guys all formed due to the Sharon-Pluto impact formation. And what they are is remnants of semi-differentiated bodies, and they're almost pure ice. I mentioned this before. I think for the interest of time, I'm going to go quickly through it. Pluto, this is a really nice bit of work by James Keane and Francis Nimmo in 2016 in Nature. And as I mentioned, what happened, we think, is that the impact and typically impacts, the impactor is about 1/10 the size of the basin you see. And you can see that Sputnik Phoenicia is rather oval, so it most likely didn't come in straight down. It came in a little bit angled. And this happened on early Pluto, and it happened somewhere, if you will, somewhere around here. And then Pluto, and then eventually it filled in with nitrogen, which is denser nitrogen ice than the surrounding material. And just because rotational energetics, the lowest energy state is if you take the most mass and put it at the equator, you increase the moment of inertia to its largest value, is its lowest energy state. So slowly but surely, Pluto would tip over and put Sputnik Phoenicia along the equator. We can tell, as I mentioned before, about the fact that we only see extensional geology, geomorphology, and the fact that we saw this rotate towards the center. We can get a rough estimate and we know the properties of nitrogen ice and the underlying water ice. We can get an estimate for what we think is inside Pluto, and the fact that the moons are also bright. We think that Pluto is actually rather differentiated, and that there may be a silicate core. And this gets really amazing. We're still arguing over this. Nobody's actually seen the smoking gun, but there's a lot of independent lines of evidence. Pluto, it's possible Pluto has a subsurface ocean of liquid ice, of salty liquid water. And that would explain why it's so round. Oops. So this is a fantastic result. I certainly didn't expect to find any evidence for a water ocean as far out as Pluto, where the surface temperatures are about 40 Kelvin. Water ice doesn't even think about subliming or getting liquid or gaseous until we get to 120 Kelvin. And remember, before we did any of this reconnaissance by Pluto, Pluto could have just been a cold, dead ice ball at the edge of the solar system. But look at all the things I've just told you already, and I'm still scratching the surface. So highlights. an active world with Pluto, with an exobase Mars-like atmosphere, we really haven't touched on very much, which has falling haze, which could leave dark regions on the surface. It has nitrogen and methane in that atmosphere, which can interact with the snow haze. It has orbital and Montage cycles, which I haven't touched on, but Pluto can sometime every few million years can warm up like crazy when it comes near perihelion, and it's pointing one of its poles right towards the sun. It has cryo volcanoes, which means there must be some sort of internal heat source. It is likely differentiated and likely has a subsurface ocean. Again, we're very far away from a cold, dead ice ball at the edge of the solar system. It has hundreds of observed craters. It has giant Sputnik planitia filled with nitrogen and carbon monoxide at low temperature. It has convection cells, migrating water ice blocks. I didn't even talk about that. We see pieces of what looks like floating water icebergs in the denser nitrogen ice and Sputnik planitia. I also mentioned it has polar wandered its giant impact basin to the equator. Sharon is half of Pluto's size. Its atmosphere is a very different looking world. As I mentioned, synchronously locked, round, and most likely frozen through its center. And in the little moons, very high albedo, formed most likely when Sharon was formed by a giant impact. And by the way, giant impacts don't just happen in Pluto and Sharon. That's how we think we formed our moon. Whenever you see a moon, there's a good fraction of the size of the primary. In our case, our moon is 1/4 of the diameter of the Earth. We pretty much think it has to be formed by impact. So, okay, we fly by Pluto, we do all this fantastic science, and we realize we have about, remember, we had about 60 or 70 kilograms of maneuvering hydrogen fuel left. We're heading into the Kuiper Belt. So first thing to do is see, is it possible for us to have another flyby? We've learned how to do flybys. We've done Jupiter and Pluto by this time. Well, we wrote a proposal to do an extended mission. We got 200 orbits of Hubble time, which, and if anybody knows Hubble, that's a ridiculously large amount of time to go and find another object. We also used our onboard Lorry camera to search deep. The problem was we were searching, I remember, okay, so skip over this. This is our field. Our Pluto, as seen from the Earth, is a few degrees off the galactic plane and within about 10 degrees of the galactic center. This is not where you want to be looking for very faint little things. But we have some really good people on the team. Mark Bowie is just and John Spencer, just extraordinary at removing all the bright objects you see in here. And this was a processed image, and this is how we found Arrokoth. We found two objects, PT1 and PT3, potential target 1 and 3, as they were called, that we could fly by given the fuel that we still had. And another way to put it is we got almost all our kick, all our velocity by launching from Earth on a giant rocket, flying by Jupiter really close. We only had a little bit of fuel in a tank that we could change from exactly the ram direction a little bit in a cone, small cone, of just a few degrees either side. And we were lucky and found something right in front of us, almost right in front of us. So Arrokoth, MU-69, a much more challenging flyby than Pluto. This target was 80 times smaller. So if you want to get an idea, here's Arrokoth. That's Sharon, which is half the size of Pluto. We came much closer to it, which means we had to get really good at flying and understanding our orbit and its orbit. And this is an object that was only discovered in 2014, which means we really had to understand its orbit very quickly. And thank God for Hubble and Gaia. The European mission did all kinds of astrometry on millions of stars. This is an object that was discovered in 2014 and flown by 5 years later. So that's quite a record. Unknown environment. We had no idea if it had gas and dust around it. It's much darker than Pluto and Sharon, which means we had to really push our detection to the limit. We had to really understand our cameras, and we did our best. A lot less spacecraft power and 12.25 hour round trip light time. So we had to do everything way in advance. Okay, here's Ultima Thule. Excuse me, it used to be called Ultima Thule. It's now Arrokoth. Here is the raw image. Here's processed. You can actually hopefully see. And here is star subtracted. This is the thing that you're trying to find in this mess. And it's just a credit to the team and to the kinetics who helped us drive by how well they did. Long story short, we did a good job. We got there. This is the image montage as we're flying up close. You put them all together, this is what, and you put them to the same ratio, the same relative size, the same size. This is what it looks like. We saw a body that was spinning with roughly a 16-hour period. And it was driving us bats because it had no light curve as far as we could tell. We tried to find it. We did occultations from the Earth. I personally went down to Argentina with 50 other people, and we got a fantastic occultation that showed us two different lobes. And we were trying to figure out how the light curve couldn't have almost flat within the noise. And the short answer is, I happen to have some 3D printed Aracloths here. Is the object, I'll show you the colored one, probably easier to see. The object was literally, as you were looking straight at it, it wasn't doing this, it wasn't doing anything like that. It was literally just doing this. It was spinning perpendicular. So the pole is looking almost straight at you. And that was a very special circumstance we were surprised to find. Lots of things in Aracloth, again, I'll speed up here a little bit. It's an object that looks like a contact binary. Two different lobes connected by a neck. There did not and does not seem to be much in the way of damage. They look like they attached very gently. So we immediately got the idea that this looks like two different planetesimals that got merged together at low velocity, slower than you walk, maybe a meter per second. Here's a stereo view, which we got by flying by it. You're seeing the front and then turning around, and this is just the very edge. We're now looking at the night side, and we're almost seeing just the edge here. But this edge allowed us to really constrain the volume and the flatness. And rather than two balls, which we originally thought when we were just looking at the front, we learned that really it's actually quite flat. And it's interestingly, not only is it quite flat, but it's actually connected along the axis of rotational symmetry of these different lobes. That's really a smoking gun, as I mentioned before, and because the neck shows very little damage, for two bodies that were most likely in doing this, coming together slowly, and then eventually locking. So a contact binary that became one body. We searched for moons because moons, we find any moon at all, it gives us an idea from just Keplerian laws of Kepler's orbits. We immediately can get a mass. Didn't get it. Nothing there as far as we could tell, the limit of our measuring. We looked, I did a lot of work on this. We looked for coma, dust and gas around MU69. Saw none. Let me see if I can back it up. You look really hard, this really is just dark sky. There is nothing. This is a body with a vacuum around it as far as we can tell. So nothing like we saw for Comet 67P. Not totally surprised because this is a body that's been in the same place for 4.5 billion years. If you work out, these are curves of Clausius-Clapeyron equation. This is my paper from 2021. If you work, and Randy Gladstone's and mine from 2022, if you work out, you expect that all the hypervolatiles like carbon monoxide and nitrogen and methane, all the pure places like that should be long gone. But everything like water and methane and methanol and HCN and ammonia, they're fine. They're just locked up and they act like rock. And so we didn't expect it to be active, and lo and behold, it isn't. Another idea is that if it was active, it would be gone by now. It would have been, because it's been sitting there for 4.5 billion years. So what New Horizons did do, slight aside, is with its student dust counter going out, it actually detected, I mentioned before, the Kuiper Belt dust. This is the dust count rate going through the asteroid belt, which should just come here and die off. We didn't measure that. We measured a giant plateau and this is due to the Kuiper Belt dust. And then we think it's starting to fall off. So it's exactly what you expect for a second source region of dust going around the sun. Here's the spectrum we saw for MU69. That's this black here. It's a bit noisy. We had all of 200 pixels across it, and we have very fast flyby. We have just literally gotten new data down. Remember I mentioned that solid state recorder and how slow it gets read out. I just heard this last week in a new science team meeting that there is additional spectral data that'll help us clean this up, and we're hoping to get some more features. We know that there is methanol. That's what these features are. We expected a nice dip due to water. We don't really see it too much. Right now, we're seeing a spectrum that looks like it's methanol and tholins, and the turnover is likely due to water. What is overplotted here is also a spectrum of Pholus, which is a very distant centaur. Remember, I told you that Kuiper Belt objects go in to become centaurs and then become short period comets. And also a Plutino. So an object that is like small, but in the same orbit as Pluto. And they all have roughly the same spectrum. And that's very interesting. You've seen three different bodies on three different kinds of orbits, but all very distant and far away from the sun. And it looks like there is thermal control of their surfaces. They're all seeing roughly the same thing. We're not surprised that MU69 has no atmosphere because we just figure out the diameter of the body versus the local temperature. This is work done first by Schaller and Brown, and also done by Zonnelly, myself, Jordan Steckloff. MU69 just isn't big enough to hold an atmosphere, whereas Pluto over here, no problem. And Sharon, kind of on the border, but still atmosphereless. Almost done. Building planetary systems. You saw me talk about this before at the beginning of the talk. We have giant rich disks. When they've stopped throwing stuff onto the star and building the protostar, they'll start collapsing themselves and they will start making planets, asteroids and comets and centaurs and KBOs and eventually planets. I'm motivating this because how do we make KBOs? I already mentioned a little bit that we think that this was two objects that stuck together. Well, the idea is that in this disk, which is orbiting around the star, you can have regions that nature is messy. Everything is not just moving in perfect lockstep. There can, for example, be sound waves. There can be oscillations where you can have places where there's lots of density can vary on the gas and the gas will pull the dust with it. And I'm going very quickly and telling you what is called the streaming instability. You can have in that disk what look like different streaks or striae and regions where the density is larger and smaller. And because it's spinning around the star, if you look closer and closer, you can actually get regions where you get little dust devils. You can get places where the stuff can start collapsing and spinning really rapidly. And you can actually, if there's enough mass, you can overcome the local viscosity and pressure, and you can start collapsing into bodies. And that's what you're seeing here. This is Nesvorny's work from 2019. And so in pictures, this is how we think we formed Mu-69. You've got one of those dust devils, you made lots of little pieces of bodies, and over time, they will aggregate and they will collapse and they will throw angular momentum by throwing other pieces out and eventually be left with two survivors, which will come together and stick. So what I'm holding here, what we saw with Mu-69 is telling the fact that all the axes are lining up, the fact that they're flattened, the fact that it looks like there was very little damage to the center is all indirect but wonderful arguments for bodies that went through this process. And if you remember, I don't know if I have the slide here, we have now imaged 5 of 7 comet nuclei. They all look bilobate like this. Fascinating. This is Bill McKinnon's work and James Keen's work to try and figure out the density since we didn't get a mass measurement. Our best estimate, if you just look at slopes, is something like 0.235 grams per centimeter cubed. The canonical number for comets is more like 0.5. That is allowed in this analysis. So we're going back and forth on those a little bit. The body doesn't, Mu-69 doesn't look unreasonable in its density. And that's what this plot is here. And what's important about that is these densities are low, and this is what you expect if you just loosely took a bunch of snow and dust and gas and kind of just loosely put it together in the beginning of the solar system, not if you compacted it like you do with a snowball and melt it. That's what happens when you get up to Pluto and Sharon. They're actually big enough that they'll start densifying and changing over their stuff. Most likely Mu-69 is an unprocessed body. If you will, as a student of comets, this was actually the most primitive and most interesting comet flyby I've ever seen, comet nucleus flyby. Colors, the colors of these two guys, even though the colors of KBOs can vary quite a bit, these two are almost exactly the same color, which is very interesting. Again, is an argument for the fact that they were formed together and stuck together. And remember, I'll skip over that for now. Just mention this. Here's our color, roughly reddish, with a little bit of different color at the neck. Almost done here. You saw this picture here. Here's the other comets. I wanted to show you 3 comets, all bilobate, just like Mu-69. Oh, and the other thing I should say really quickly, the size. Mu-69 is about 33 kilometers this way and 17 this way, and then actually rather thin, 5 the other way. It's much bigger than these objects. So it's about a factor of 10 bigger than they are. Geologically rich, you hang out with geologists, they can't just look at a picture and not show you all kinds of different regions. The so-called monkey bread is important to me. The larger lobe looks actually like it's got made of a whole bunch of different pieces. And we think that maybe these are some of the smaller pieces that gang together to make the big one. On the other hand, the smaller lobe actually looks like it's relatively uniform, and it has a big crater in it. So I'm going to skip over this in the interest of time, but I'm going to show you is that there's lots of interesting structure here. And there is also chains of pits, which we think might be due to some of those, I mentioned hypervolatiles that may have formed very early when things were dark and cold in the accretion disk, but then as soon as it cleared out and the sun warmed everything up, they came out. Here's Rosetta's target, just for scale. Here's your distant flyby. This is James Keen's. I think I will skip over this. And this is what 67P, the Rosetta target, looks like. This is what our guy looks like, very quiet. But they are similar and they do have interesting structures in it. Highlights, as I mentioned, 2 pieces, pronounced neck, attachment along symmetry directions. This object is as big as the biggest comet we've ever seen, which Hale-Bopp's nucleus. Actually, UN-271 has come along. It is smaller than the biggest comet we think we've ever seen, but it's on the order of its size. It is in between. This is in between size between a comet nucleus and a dwarf planet like Pluto. 1 big impact crater, many small depressions and pit chains. As I mentioned, moving slower. It's connected, but in 16 hours like this. Slower than a contact binary. Somehow, when those things came together, they had to throw away angular momentum. And so maybe they came together and there was still some gas surrounding them. Mentioned the co-creation, colored lobes, stream instabilities. The other thing, maybe I didn't mention enough, this object was formed 45 AU from the sun and has stayed there the entire age of the solar system. So this is a relatively, probably the most pristine piece of material humankind has ever encountered to date. No moons, no activity, and I mentioned what's on the surface is a little surprising, but looks not if you believe in thermal stability. Okay, are we out of time or can I talk more? I guess it's only me. Okay, so let me show you what some of my recent work that I've been putting this all together. I asked the question that if we have Pluto, which I showed you has this beautiful heart and has lots and lots of hypervolatiles, has lots of CO, lots of methane, lots of nitrogen. You can see these maps, but we see none of that on Arrokoth. Arrokoth just looks like methanol and tholins and maybe hints of water. So how do you make Pluto if you made Pluto out of millions and millions of these? Just build it from up. You make these guys first. Well, the obvious, and we think that Pluto's got lots. Also, Pluto we mentioned is differentiated. The best guess is that you make Pluto so fast. There's 3 different ways. You can make Pluto so fast that Mu-69-like bodies didn't lose their hypervolatiles. And what we're talking about, the time era is when that accretion disk is thinned out and suddenly we call it morning has come to the Kuiper Belt. The sun can illuminate and can warm things up. You go from the 20 degrees or so of the very optically obscured thick accretion disk centric core, and suddenly you warm up to Pluto's, Arrokoth's current temperature is somewhere between 40 and 60 degrees, depending on whether you're at noon or not. And so you're going to lose all your hypervolatiles real fast, but you still have a bunch of years. So you can do it really fast, make Pluto, or you form Pluto so fast that the gases that leak out of Arrokoth are still around in the circumstellar disk and they haven't been thrown away yet. And that takes about 10 million years. And so these tell you can form Pluto fast, or ignore all that. Take your time, make Pluto as slow as you want. Don't worry about getting any of the gases from little guys. Well, instead, totally differentiate Pluto through and through. Make Pluto perfectly able to mix. It's melted. All the dense stuff has fallen to the center, and all the really light stuff, the nitrogen, the methane, the CO, just like the water did on the Earth, we think, has come up from the inside and has bubbled to the surface and reformed very beautiful light ice-rich surface. And Pluto is big enough now, it can actually gravitationally hold on to those ices. So as far as I can tell, you have these 3 different, and then the modelers can have a good time with this. It's also been pointed out that when Sharon hit Pluto, and most likely blew away any surface, and it had to reform. So I'm really liking this number 3 one right now. I think we've got a lot of impetus for Pluto being differentiated, having a subsurface ocean, and resupplying the ices you see on the surface from the interior. Okay, this slide is for those people, I'm not going to read it, but it is for people who are interested in everything I've talked about, and I told you that I had to skip over. These are the names and these are the different science topics. So the audience is welcome to these slides, and hopefully this will help them do some research. I want to point out that New Horizons is an extremely healthy spacecraft, and you can go to this webpage and you can find out today where Pluto is right now, and I'm about to show that to you because I just did that before this talk. And New Horizons has plenty of heliospheric science as it heads out toward the edge of the solar system. It is the farthest out inside the heliosphere, inside the heliopause. The Voyagers are outside that. They're actually in nearby interstellar space. We are looking at Kuiper Belt objects from angles and directions that you can't see from the Earth. We are still hoping to find another flyby target, but it's getting kind of dicey because we're going through more than half that Kuiper Belt. And estimated power right now, as I mentioned, now 2030s, about 100 AU from the sun. These are the distant KBOs that we're doing some fantastic work. And we can look at them from the Earth, and then we can look at them from back and from the side, and from phase studies and from light curves. We can learn a lot about what they're made of. We can find binaries that way. And we're finding a lot of similarities in the small guys. Here's the plot, as I mentioned. We are currently, New Horizons right now, we are here. We are currently 53 times the distance from the Earth to the sun. We are 10 AU past Arrokoth. And so we are in the heart of the Kuiper Belt. And for truly brave dreamers, we would like to go back and actually orbit or land on Pluto. We've been talking about that a little bit, and that's the end of my talk. And I will thank you all for your attention.
Yeah, thanks, Casey. Very interesting talk, and I have a lot of information there.
There is. I apologize if it was too much, but again, the slides hopefully will help people if they want to do some more study.
I think there's the way you are. You know, there's no way to stop you, right?
Well, hopefully the excitement of the exploration came through.
Oh yeah, I mean, just by seeing you, is enough. Let me see. We still have about, because the next talk is to come out at 10 o'clock, but we still have perhaps now one question. Any question from the audience? I think Casey gave you a very, kind of, comprehensive oversight. Yeah, go ahead, Zhongyi.
Okay, I'm Zhongyi. I did have two questions, but any question is for the Pluto 4 little moons, why can we make conclusion that it's not from the capture? I mean, they are from the impact instead of the capture.
That's a really good question, which I didn't go over very well. So Pluto, I'm going to go back, get out of this. The moons are actually spaced incredibly regularly. Let me see if I can pull it up. They are all in, if you look at Sharon, they are all spaced at 2 to 1, 3 to 1, 4 to 1, and 5 to 1 resonances with Sharon, how Sharon goes around, and Sharon and Pluto rotate. And if you try to figure out how to do that, you wouldn't, and also the way that they spin, you would not expect them, if they were randomly captured, to fall into those orbits. I'm trying to see if I can find it. Yes, I think I have it here. So this is something that you would have to do a dynamical study, like Hal Levinson has done. So these orbits are actually not random at all. They are spaced incredibly regularly. And Sharon is controlling Sharon and Pluto are controlling how they orbit around the binary planet system, if you will. And so and they're also in a plane. These are all things one would expect if there was a giant impact, and which brought in and set the angular momentum for the system. The other thing that I mentioned rather quickly is these are all 60 to 70% albedo. They're really bright. Pluto and Sharon are not that bright. And so, as you can see, they've got large patches of very dark material. They've got methane on the surface. These are consistent with almost pure water ice, which is what you would expect if you had a semi-differentiated body, a body that was kind of not just pure random mix, but also kind of homogenized, but came in and hit a semi-differentiated object that had a lot of water ice near its surface. So we think that these are actually, otherwise they would be just random. So they should have all the elements you see here and here. So for those reasons, and they're also very small, which would argue that if you heated things up really hot in an impact and then try to condense down, only the most refractory ices, and those curves I showed you, all the toughest ones that boil at the highest temperatures, which is water ice, would be in the moons. So these are all arguments for why we think an impact happened. There's really good work by Robin Canup, if you'd like to read it, about forming.
Thank you. Just one last question, a very short one, hopefully. Lin Qihong, you want to ask the question?
Okay, so good morning, Professor. So I have one question. So just like you say, so the Charon and the Pluto, this is a one-teddy block. So when they are rotate each other, the Pluto, they will also be shaking. And just like you say, it says the Charon also has 3 little satellites around the Pluto. So my question is, when Pluto and the Charon are tightly locked and they are shaking, will they affect the orbits that's the 3 small satellites? So that's just my question. Thank you.
I think if I understand correctly, you're asking a good question. You're asking what happened when the impact first happens, and then how they settle down and stabilize. And you're asking a really good question, which I only know enough to get in trouble here, as I said. One of the first pieces of work I did in this mission was to figure out what deviations Pluto and Sharon had from spherical. And it's almost none. We cannot detect anything within the error measurement. That said, the only way we can do that, and Sharon, remember, when it first formed, Sharon isn't where it is now. Sharon was like here. They were literally almost contact binary, but spinning really fast, and Sharon has been slowly moving out due to tidal interactions, just like our moon is moving away from us. And in order for them to not look like eggs, to actually have a bulge, Pluto and Sharon, if you would expect, would have a bulge. They had to stay liquid. They had to stay fluid until Sharon moves out as far as it is now. And so that tells you that both of them probably had subsurface oceans and were plastic. We think Sharon, just the same way that it's too small to hold an atmosphere. They may have been in this quaking, there may have been geological changes I mentioned, but Sharon, we think, is now frozen. And the last thing I'll say on this, whereas Pluto isn't all the way inside. The other thing I'll mention really quickly is that Sharon is about the same size as Ceres, that the biggest asteroid we have. And so I've asked the question to people who modeled the interior of Sharon and Ceres, Steve Desch, for example, why are they different? And the short answer I got was that they may have very similar compositions, have a similar amount of radioactives, but Sharon is in a much, much colder place. So it lost its heat faster. So it's interesting to think about. This is about the same size as Ceres.
So that's the 4 small satellite, their orbit will not shaking by the Pluto and the Sharon. They will be kept stable.
Oh, you mean what? When you mean rotating?
Yeah.
I understand the word shaking. Oh, yeah, they're very stable. Yes, and the fact that the other moons are all in resonances, this is 2 to 1, 3 to 1, 4 to 1, 5 to 1, tells you that the spin, this whole system is coupled, which is fascinating. They're all moving in sort of lockstep. I'm not trying to say that these guys are always all in a line. They move around at different rates than these guys are coupled, but they are all moving in 2 to 1, 3 to 1, 4 to 1 resonances. So yes, the spin of Pluto and Sharon is controlling the whole system.
Okay, thank you, Professor.
You're welcome.
Okay, Casey, thank you. We have the next talk coming up, and you're welcome to stay on, ask questions.
I'd like to listen.
Thank you, and until next time, and I hope to see you soon also.
Yes, that would be nice. We'll be talking.
Yeah.
I will mute and turn my video off.
Yeah. Bye.